Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Take a moment to look through the nearest pane of glass. It's hard, rigid, and seems utterly permanent. If asked to define it, you'd likely say it is a solid. And by all common definitions, you'd be right. Yet, physically and fundamentally, glass is a substance trapped in a state of permanent existential crisis. It is the definition of an amorphous tyranny. A substance that is rigid enough to fool us into thinking it's solid, but disorganized enough that it is, scientifically, always falling. To understand this paradox, we must first look at true solids. Consider a diamond or a common table salt crystal. Their atoms are arranged in a precise, repeating, geometric pattern, a crystalline lattice. When these materials melt, their highly organized structure collapses. When they solidify, they snap back into that perfect order. Glass, however, defies this elegant order. Chemically, most common glass is silicon dioxide, or silica. But when molten silica is cooled, it cools so rapidly and its constituent molecules are so tangled that they never have time to line up into a lattice. Instead, the atoms freeze mid-flow, locked into a chaotic, disordered arrangement that more closely resembles a liquid. This state is called an amorphous solid. For decades, physicists famously referred to glass as a supercooled liquid, a liquid cooled below its freezing point without crystallizing. While modern material science favors the term amorphous solid because of glass's incredible rigidity, the core concept remains. Glass lacks the structural discipline of a true solid. It is, fundamentally, a very, very slow liquid. This leads us to one of the greatest enduring myths of material science, the flowing church window. If glass is always falling, then surely ancient cathedral windows, some hundreds of years old, must show evidence of this movement. The common wisdom states that old stained glass panels are measurably thicker at the bottom than the top, a clear indication that gravity has slowly dragged the material downward over centuries. This image is evocative, but the science doesn't hold up. The thickening of these historical windows is almost entirely due to primitive manufacturing techniques. Before the development of the float glass process, glass panes were often made by spinning molten glass into a disc, a process that naturally resulted in uneven thickness. Glazers, always practical, installed the thicker, sturdier edge facing down for stability. If glass truly flowed enough to be noticeable in a few centuries, imagine the astronomical viscosity required to slow that process down. Viscosity measures a fluid's resistance to flow. Water has low viscosity. Tar has high viscosity. Glass has a viscosity so immense that it is almost beyond human comprehension. Calculations suggest that for glass to flow enough to visibly thicken a window pane by even a millimeter would require timescales on the order of several millions, if not billions, of years. Your kitchen window is not going to suddenly slump onto the floor. However, the idea that glass is perpetually falling or relaxing is still technically accurate on a molecular level. Though the flow is imperceptible, glass is constantly undergoing structural relaxation, a phenomenon driven by the material's desire to reach its thermodynamically favored state. Since glass is trapped in a non-equilibrium state, its molecular structure is trying, ever so slowly, to rearrange itself toward a more stable, and often crystalline, form. The defining feature of glass is the glass transition temperature, or Tg. Below Tg, the material is rigid and appears solid. Above Tg, it softens dramatically and becomes clearly liquid. Unlike true solids, which have a single, sharp melting point, glass transitions gradually, becoming softer and softer as it heats up. This transitional flexibility is exactly what makes glass so useful for everything from fiber optics to windshields. we can shape it precisely before it snaps into its rigid, chaotic, non-equilibrium structure. So, while the architectural myth of slumping windows is largely debunked, the core truth remains. Glass is stuck. It is a disordered, amorphous substance trapped by cold, enduring the tyranny of a state it never truly achieved. It is a solid only in the sense that its molecules are moving incredibly slowly. It is the epitome of frozen chaos, forever attempting an escape that gravity will only grant over geological time. The window you look through is not truly a solid, it's an impossibly slow river of frozen silica. For more incredible facts like this, don't forget to subscribe and turn on notifications.